So our last speaker for this session today is going to be Son Ho, who is going to talk about the soundness of Rust's borrow checker.
Okay. Hello, everyone. I'm going to talk about the semantics of Rust, and in particular, the Rust borrow checker. So let me give you some context about Rust first. So Rust is a low-level programming language which provides memory safety without using a garbage collector. And it does so in particular by using a special mechanism called borrows. We can illustrate borrows with the following example, which is this max function, which takes as inputs two mutable borrows of U32 and returns one mutable borrow. A mutable borrow is a kind of borrow, so there are different kinds of borrows. And it can be seen as a pointer, which gives an exclusive read-write access to the value it points to. So here we're simply receiving two pointers. We compare the values of the two pointers, and depending on the result of this comparison, we return one of the two. Now, an important element is that those borrows are annotated with a lifetime alpha. And what this lifetime tells us is that for as long as the output borrow is alive, we have to consider that those two input borrows are alive, and so they borrow their values. So let's see this on this example. Here we call the max function by giving it two mutable borrows to x and y. And in return, we get a borrow z that we can use to do an in-place update. And then later, at the assertion, we can get access back to x and y by, for example, asserting that y isn't changed and x isn't changed and y has been updated. And an important point is that because of the lifetime constraints here, for as long as the borrow z is alive, we have to consider that those two borrows of x and y are alive, so x and y are borrowed, and we can't access them. This means that in order to evaluate the assertion, we have to end the borrow z just before. So in particular, this means that the lifetime alpha starts from the call to the max function and ends just before the assertion. And this lifetime alpha is statically inferred by what is called the borrow checker. Now, you might be tempted to use z again afterwards, but if you try to do so, the borrow checker will tell you, no, you're not allowed to do that because we had to end the borrow z earlier. Okay? So this provides a quite expressive language and memory safety at no runtime cost. And this, along with other design choices, has made Rust an extremely popular programming language, especially in the industry. But there is a small issue, which is that the borrow checker is a quite complex beast, and there is no official formalization of the borrow checker, and there are no formal guarantees that it indeed provides memory safety. Now, there is no official formalization of the borrow checker, but there are proposals. In particular, 2 years ago, we presented a paper at ICFP in which, among other contributions, we introduced two things. One, the low-level borrow calculus, or LLBC, which is an operational semantics for Mir, where Mir is one of the internal languages used by the Rust compiler. And the low-level borrow calculus has a specificity, which is that it does not explicitly model the memory. And two, we introduced a borrow checker for LLBC, which is based on some sort of a symbolic execution. Now, there were some caveats. In particular, LLBC uses a non-standard model for borrows, especially because it does not explicitly model the memory of your program. And also, there is no proof that the borrow checking through the symbolic execution indeed provides memory safety. And we could not actually state it at all because LLBC does not explicitly model the heap. So in the present work, we formalized this problem and addressed this problem by formalizing and proving the fact that if you have an LLBC program which borrow checks according to the symbolic borrow checker, then your program is memory safe to execute. And by memory safe to execute, I mean that it is safe to execute for a language, a more standard language, which explicitly models the memory by using a memory model inspired by CompCert, and where borrows are simply modeled as pointers. So if you have one result to remember from this talk, this is this slide. And now I'm going to get a bit more into the details. So a key element from the work we presented 2 years ago is the low-level borrow calculus. That is this operational semantics for Rust. And it has the peculiarity of not explicitly modeling the memory. And in particular, it represents program states as environments, that is, as mappings from variables to values. So for example, if we execute this snippet of code by using LLBC, initially we just have an environment where we have a mapping from variable x to the value 0. And then we evaluate the mutable borrow. With LLBC, when we create a mutable borrow, we say that the borrow takes the value with itself so that it can read it and update it. And at some point later, when the borrow ends, we give the value back. So here, we take the value of x, that is 0, and we put it inside of p, and in particular inside the mutable borrow wrapper, which tells us that p mutably borrows the value 0. But we also need to link x and p somehow. And we do so by updating the value of x to some mutable loan value, and by introducing a fresh identifier L0 to link the mutable borrow to the mutable loan. So in this environment, we get that either x is mutably borrowed by p, or that p mutably borrows the value 0 from x. Okay? And then we can continue. For example, on the next line, we do an in-place update, so we look up the value of p, we evaluate the dereference by diving into the mutable borrow, and then we update the 0 to a 1. And finally, we get to the assertion. Here, we need to read the value of x. But x has been mutably borrowed, so it does not have access to its value anymore. In order to get access back to this value, we need to end the borrow. When we end the borrow, we simply look up the corresponding value, and we put it back where it was. So here, we take the 1, and we put it back inside our x. So now x maps to 1, we can evaluate the assertion, and p maps to some bottom value, which means that its value is not valid anymore. You cannot do anything with it, and in particular, you cannot dereference it. Otherwise, you would get a borrow checking error. Now, there are many other things to make this work. In particular, we need to account for shared borrows, two-phase borrows, etc. But an important point to mention is that when we have a function call, of course, we dive into the function body by pushing a stack, evaluating the function body, and popping a stack. When you put everything together, you get an operational semantics for Rust, which is centered on its system of borrows, and which is lazy in the sense that we end borrows as late as possible. So here we end the borrow p only when we need to get access back to x. Now, an important observation to do is that function signatures in Rust, due to the lifetime annotations, give us another approximation of the behavior of the function body. So we can use those signatures as summaries to abstract the function calls. And this is actually what the borrow checker does. And in particular, if you tweak the semantics of LLBC to abstract function calls so that when you have a function call, instead of diving into the function by pushing a stack, evaluating the function body, and then popping the stack, you instead use the signature to over-approximate what happens. You get something we call the symbolic semantics. Now, the conjecture from the previous paper was that the symbolic semantics can be used to define a borrow checker. More precisely, if we symbolically execute every function in a program P, and the symbolic execution succeeds, in particular, it does not get stuck because, for example, at some point you need to dereference a borrow which you had to end before, that is, you dereference a bottom value, then your program is memory safe. So what this means is that you just take your program and you symbolically execute all the bodies, the function bodies in this program, and if it succeeds, if the symbolic execution doesn't get stuck, then your program is borrow checked. And because the symbolic semantics abstracts function calls, we do not dive into function calls, this is a modular analysis, so this works very much like tab checking. Now, this was a conjecture. And in order to prove this conjecture, there are several challenges. The first one is, in order to prove memory safety, we need to talk about the memory, and it is non-trivial to link LLBC to a more standard semantics which explicitly model the heap. So, for instance, we introduced a more standard semantics we call the pointer language, which uses a memory model inspired by CompCert and in which borrows are simply modeled as pointers. That is, the value of a borrow is an address. So, in this example, after we evaluated the second line, we will get a state where x and p map to some memory blocks, and the memory block of x contains the value 0, while the memory block of p contains an address, which is actually the address of x. Now, this state is actually quite different from the environment you get with LLBC, where in particular, the 0, the value of x, lives with p, while here, p points to 0, which is inside of x, okay? So here, this is a small difference, but when in the presence of something which is called reborrows, which is very common in Rust, it can lead to a very big discrepancy. So this is the first challenge. The second challenge is even after we manage to make a link between LLBC and this pointer language, we need to make a link between the symbolic semantics and LLBC to actually prove that our symbolic borrow checker gives us memory safety. So I don't have the time to give you all the details about how we did that, but with those elements of context, I can give you the more formal statements that we proved, which is that if we successfully borrow check a program by using this symbolic borrow checker, then one, this program is memory safe to execute according to the pointer language, and two, the semantics of the pointer language and of LLBC are in BC emulation on this program. So this is the main result of the paper, and it is mostly a soundness result. Now, we also built, on top of this result, to extend the symbolic semantics we defined so that we could handle a larger class of programs. So let me explain you the problem. A crucial element of the symbolic semantics is that we can use function signatures which give us summaries. But there are situations where we would like to abstract away what happens, but we can't. We don't have a summary. For example, if I inline the function max, I approximately get the following. So I've got this if then else. And we would like to approximate what happens here. In the previous version of the symbolic execution, what happened is that we had to split the control flow. So we evaluated the then branch, then the continuation here, and we also evaluated the else branch, and again the continuation. So we had to evaluate the end of the function twice. Now, by taking some inspiration from abstract interpretation, we introduced and justified a join operation, which allows us to join the two environments from the then and the else branch into one more general environment, which then allows us to execute this part of the function only once. So this avoids having a combinatorial explosion in the context of branchings. And in a sense, the join operation, which we proved correct in some sense, allows us to account for the lack of summaries for if-then-else branchings. And we went further by using this join operation to add support for loops, once again by taking ideas from abstract interpretation. So in particular, we can use the join operation to compute fixed points for the loops, which we can use to compute a general environment for the end of the loop from where we can continue the execution. And this allows us to account for the lack of summaries for loop bodies. So, as a conclusion, the main result of the paper is this soundness result, which is that if you have an LLBC program which successfully borrow checks according to the symbolic semantics we defined, then this program is memory safe. We also extended this symbolic semantics with a join operation, which allows us, in particular, to add support for loops. Now, there are many details in the paper, and in particular, the proof relies on a series of simulations between a sequence of languages. And in order to make that work, we had to introduce novel techniques to make such simulation proofs. We consider a subset of Rust, of course, but an interesting subset with many features. And in particular, this is an auditory language. We have an implementation of this borrow checker, and it runs on real Rust programs. Now, this symbolic execution, which is at the base of the borrow checker I'm presenting here, is also at the base of the Aeneas verification framework for Rust programs. And I'm giving you a tutorial about it tomorrow, so if you're interested in that, please come. Thanks for your attention.
Hello, I'm Charlie Libri from Imperial College. When you do the join operation between environments, do you ever lose information in that join, and does that ever cause it to reject programs that didn't need to be rejected?
So, so we have to do some approximation. So for example, if you have some value which becomes invalid in one environment, so it becomes bottom, you have to consider that it also becomes bottom in the other environment. So far, we do not have, we have something which is quite precise. So in particular, there are many programs we can't handle because we don't have the features. But there are some Rust programs that are rejected by the current Rust borrow checker because it is not precise enough, but that we manage to validate with our technique.
Cool. So the joining doesn't introduce any lack of support.
So far, it seems to be quite precise. Yeah, but we still need to evaluate that on more programs and on a larger class of programs.
Thank you.
Other questions? Yeah, I was curious, how does it compare to Rust's own borrow checker?
Yeah, so it works quite differently. Once again, there are many features we don't have yet. We're working on that. So there are many programs which are accepted by the Rust borrow checker that we don't accept. But once again, there are also some programs that we manage to validate, which are rejected by the Rust borrow checker, especially because the Rust borrow checker is not always very precise in the presence of branchings, specifically.
So thank the speaker.